Good day, everyone. Welcome back to Math 30-2. We're continuing on with Unit 2, which deals with permutations and combinations, or what we sometimes call counting methods. And we're looking at Lesson 3 today, which is titled Permutations with Restrictions. And there's nothing really new in this lesson. What we want to do in this lesson is just get more practice dealing with permutations, which are arrangements, if there are restrictions. And we've already talked about this in a previous lesson, but to go over it again, when you're dealing with permutations that have restrictions, restrictions are rules that you have to follow that are special rules, like people are going to stand in line for a photo, but the tallest person has to be in the center. Or it doesn't really matter. You can come up with all kinds of situations. We can go back to Lucy buying the SUV, and one of the restrictions could have been she wants a red or a white vehicle. The important thing to remember about restrictions is that when you start to piece together a strategy, you deal with the restrictions first. So if you use the fundamental counting principle, which is a really good strategy for many problems, you have to find the number of choices for that part that's restricted before you find the number of choices for other parts that are not restricted. And many of the problems in this lesson can be solved using the fundamental counting principle. I don't really know how many of them can be, probably all of them, but maybe not. We're going to find out. So class example 1 asks us to answer the following question in two ways, using the fundamental counting principle or using factorials. So the question is, we have the word oranges, and we're going to take all of those letters and we're going to arrange all of the letters, but there are no restrictions. Well, if I want to answer that question using the fundamental counting principle, then my strategy is to say that I am arranging, how many letters are there? 1, 2, 3, 4, 5, 6, 7, O-R-A-N-G-E-S. There's 7 letters. So the fundamental counting principle says you're going to have 7 choices to make. 1, 2, 3, 4, 5, 6, 7. The number of choices or options you have for the first decision is 7. Then you're down to 6 because you're arranging the letters. You can't use whatever letter you put in the first blank, you can't put again in the second. And this goes down 5, 4, 3, 2, and 1. And we can work that out, 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's how you would do it using the fundamental counting principle. If you use factorials, then you simply remember what we learned yesterday, which is that the number of ways to arrange all of the items at once, if there's no restrictions, is that number factorial, which we can see that's what you get. It's 7 factorial. That's what 7 times 6 times 5 times 4 times 3 times 2 times 1 is. Anyway, the answer is, I'm not 100% confident. I'm pretty sure it's 5,040. So I'm just going to pull up my calculator and make sure. 7 factorial. Pretty sure. Yep, 5,040. Now the next question asks us, the first letter must be an N. Well, if you use the fundamental counting principle, you're going to put your 7 blanks, first, second, third, fourth, fifth, sixth, seventh. You're going to write the restriction below and say that this must be an N. And then you're going to fill in the number of choices for that restricted item first. Well, there's only one N, so there's one choice. It's not even really a choice. And then we're down to 6, so it's 6 times 5 times 4 times 3 times 2 times 1. And if you work that out, it's going to be 720. Now, how would you think about this using factorials? Here's how I would think of it. I would say to myself, I have 7 blanks, and the n has to come first. So you know what? I'm not even going to worry about arranging the n. The question really becomes, how many ways are there to arrange the letters of the word orages? I mean, you've taken my input out of it. As soon as you've told me the first letter must be an N, well, what are you asking me about it for then? You already decided it's there, and that means that this is 6 factorial. And again, that's going to give you 720. By the way, you could have solved this first question by saying it's 7p7, because you have 7 items and you are arranging them 7 at a time. What do we get? 7p7. No surprise. You could have done this one by saying 6p6. And I'm not going to spend time throwing that on my calculator. You will get 720. Class example 2, 3 girls. We could give them names, but apparently this workbook doesn't want to do that. G1, G2, and G3, and 4 boys, B1, B2, B3, and B4, are going to be arranged in a row for a photograph. So there are 7 people. How many ways can this be done if there are no restrictions as to where each person stands? By the way, it doesn't say they're standing in a line, but when you get these questions, you can always assume they're standing in a line. Well, the answer to the question is 7 factorial. There's 7 people that you're arranging. It's 7 factorial, or it's 7p7, or it's 7 times 6 times 5 times 4 times 3 times 2 times 1. It's 5,040. Now, the photographer decides that it will be a better photograph if the genders alternate. So wherever you look in the line of people, it's got to be boy, girl, boy, girl. Girl, boy, girl, boy. You can't have 2 boys next to each other and 2 girls next to each other. And with a little bit of thought, you realize since there are 4 boys, and there are only 3 girls, you have 1 more boy than girl. That means you have to have a boy here and here. If you start off, I'll erase those just for a second. If you start off and say we're going to have a girl, then a boy, then a girl, then a boy, then a girl, then a boy, the 3 girls have already been seated, so we can't alternate anymore. You'd have to end with 2 boys next to each other. So that's why the restriction is that this must be a boy, this must be a girl, boy, girl, boy, girl, and boy. It doesn't really matter where you start because there's restrictions all over the place. We can start on the left. We have any one of 4 boys here. Let's continue seating the boys. That means we have 3 here. Well, we don't have 3 boys there. We have 3 boys to choose from. We're down to 2 boys to choose from, and whichever boy has not been chosen, they sit here. And this will be 3 times 2 times 1. So we're going to multiply all of these together. You can take your calculator and multiply it. I'm going to do the same thing. You should get, I think it's going to be 144. But I want to point something out to you. That what we're really doing is we are arranging the 4 boys and we are arranging the 3 girls. So there's nothing wrong with you saying to yourself, you know what? I have to arrange the 4 boys in those 4 seats. That's 4 factorial. And fundamental counting principle, and means times, I have to arrange the 3 girls in those 3 other seats. There's almost always multiple ways to think of these problems. And if I take 4 factorial, which by the way is 24, and I multiply that by 3 factorial, which is 6, I get 144. If you want to do all of the extended multiplication, 4 times 3 times 3 times 2 times 2. I feel silly saying times 1, but there you go. You get 144. If you want to say 4 factorial, 3 factorial, not sure what happened there. Do that again. 4 factorial, 3 factorial, you get 144. I mean, you could, oh man, this would be absolute overkill if you did this. But you could say it's 4 boys arranged 4 at a time, times, because it's and, 3 girls arrange 3 at a time. I realize now, everybody, that I didn't actually answer number 1. What I have answered is B part 2. So I'm never trying to confuse you, but this is the answer to 2. The answer to 1, it just said show one such arrangement. It could be B1, G1, B2, G2, B3, G3, B4. That is one particular arrangement, starting with a boy, ending with a boy, and you can feel free to change B1 and B2 around. It doesn't matter. So what I did is, I jumped the gun and I actually answered question 2. All right, class example 3, 6 actors and 8 actresses are available for a play in which there are 4 male roles and 3 female roles. Although this is extremely outdated, what we are assuming here is that the actors are going to be used to fill the male roles and the, quote, actresses are going to be used to fill the female roles. So it's hard initially for us to imagine why this is a permutation, but let's just write this out. Let's say this is female role 1, this is female role 2, and this is female role 3. So this might be the casting list that they're going to post. You know, maybe female role 1 is Pat, and female role 2 is Allison, and female role 3 is Alyssa. That's the character names. And then we have different male roles. We have male role 1, male role 2, male role 3, and male role 4. So how many different actresses can we choose for the first female role? Well, the answer is 8. And then we have 7, and then we have 6. You certainly can't have the same actress doing 2 roles. Well, I mean, I suppose you could. But in the context of this question, we don't do that. How many do we have to choose from for the first male role? Well, we have 6 actors, and then we have 5 for the second, 4 to choose from for the third, and then 3 to choose from for the fourth. So we multiply this all out, and there's a more elegant approach to this, a nicer approach. Let's see what we get here. 8 times 7 times 6 times 6 times 5 times 4 times 3. Get that right? I think so. That many. 12,960. There's a different approach, though. You could say, of the 8 actresses, I need to arrange 3 of them in those positions, in those roles. And of the 6 actors, I need to arrange 4 of them in those positions. So this is the answer to the question. I am pointing out to you that on a diploma exam or on a unit exam, that might be a choice. You might also, and it's early in the semester, but we've got to talk about these things, this might be made into a numerical response question where it says the answer is APB multiplied by CPD. What are the values of A, B, C, and D? Well, 8, 3, 6, and 4. So you'd have 4 blanks on your answer sheet. This is not blanks for a permutation. This is 4 blanks on the answer sheet, and it would say A, B, C, and D, and you could record 8, 3, 6, 4. You could also put 6, 4, 8, 3. Regardless, let's find the answer to the question using that method. We know it should be 120,960. So 8, whoops, turn that pen off first. 8, go to my math menu, P3 times 6P4, you get the same answer. Again, it's very rare that there's only one way to think of these things. Number 4, Andrew is asked to determine how many arrangements of the letters of the word brains are there when the vowels are together. The vowels are A and I. I just want to write these letters out myself. B-R-A-I-N-S. So vowels are these 2. So here's what Andrew thinks. What Andrew says is he is going to take this item, this item, this item, this item, and these 2 items and create one element, one thing. And if you look at what's at the top of the screen, I have 1, 2, 3, 4, 5 things. I have this is one thing. I have this, and I have this. I have 5. So Andrew says, well, it's 5 factorial. The first part of this says, I think there should be an A here that I didn't type in. Is Andrew correct in saying A and I should be combined as one element? Yes, he's correct. They should be. Is Andrew's answer correct? No. Because what Andrew is neglecting is he has to arrange there we go. He needs to arrange the 5 elements. That's one of the jobs he has, and he has to arrange the A and the I. Not only can he put that box with the AI wherever he wants, he has to look at the possibility of arranging the items within it. So he has to arrange the 5 major elements or major items, which is 5 factorial, and he has to arrange the A and the E, which is 2 factorial. And that's not going to give you 120, it's going to give you 240. Number 5, how many permutations of the letters of the word kitchen exist if the letters K, C, N must be together and in the order K, C, N? So we have the K, C, and the N, and these things are glued together in part A. It says they have to be in that order. So imagine that this is a set of algebra tiles, and I've taken the K and the C and the N, and I've super glued them together. I can move them around as a separate element, but I can't change the order of them within that element. I also have an I. I also have an I, a T, let's see, whoops, a T. I have an E. Did I get them all? K, I, T, oh, I have an H. So I'm just going to show you how I double check things here. I have 1, 2, 3, 4, 5, 6, 7 letters. Down here I have 1, 2, 3, 4, 5, 6, 7 letters. I've written them all down. They're all accounted for. So I am arranging this, 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 and this. Well, look at that. I'm only arranging 5 items. And this answer then is going to be 5 factorial, which will be 120. Now, why are we not considering in part A arranging K and C and N? Because in part A it says they have to be in that order. Now in part B, how many arrangements are there if the K, C, and N must be together, but they can be in any order? Well, then it's going to be 5 factorial to arrange, let me do my highlighter thing here, 5 factorial to arrange these 5 items, and 3 factorial to arrange these 3 items within that single item. And that works out to, you can check it on your calculator, it's going to work out to 720. By coincidence, that's 6 factorial. And I'm pointing that out because maybe on a multiple choice question, these are your choices, and one of the choices says 6 factorial. And you're doing some practice, and you look at that and you go, well, I don't think it's that. And you look at the back and it says that's the answer. Don't look at it and go, why is it 6 factorial? It's 6 factorial just because it happens to be equal to 6 factorial. If you really want to know the reason, 3 factorial is 6. This is equal to 6. And 5 factorial means times 5 times 4 times 3 times 2 times 1, which gives you 6 factorial. But it's basically a fluke. We have one final question to do. Frank, George, Hannah, Iris, Jacob, and Kim have got tickets for a hockey game in seats that are next to each other, A3 through A8. Let's just check something out here. A3, A4, A5, A6, A7, A8. 1, 2, 3. Yeah, there's 6 seats and there's 6 people. How many ways can they sit in those seats? Well, 6 factorial. That's it. But George and Hannah are dating, and they want to sit beside each other. So I'm going to write out the people. Frank, G for George. Hannah, I'm going to put right beside George because they're going to be seated together. I for Iris, J for Jacob, and K for Kim. I hope that you see that this is the same kind of question as the last couple of examples. If George and Hannah have to sit next to each other, we treat George and Hannah as one item, and we're arranging 1, 2, 3, 4, 5 items, which is 5 factorial, and we need to arrange George and Hannah, because George could sit to the left of Hannah, or Hannah could sit to the left of George. And that's 240. Now, the final question, and you might be asked this question without being asked A and B. So just before they walk into the arena, George and Hannah get into a fight. They have an argument. They're really mad at each other. And you know what? They are not going to sit together. They cannot sit beside each other. The question is, how many ways can they all be seated now so they don't sit together? By the way, this is 720, isn't it? Why am I asking you? I can't hear you. 6 factorial is 720. Boy, we better just make sure before I go on. I'm pretty sure on these numbers, but 6 factorial, yeah, it's 720. But I just, sometimes late in the day, I kind of go, I better check. 6 factorial, 720. 5 factorial times 2 factorial. I hope everybody recognizes I don't have to go 2 factorial. I could just go 2. That's 240. So the only way you can find out how many ways they do not sit together is to understand this. Of the 720 different arrangements, some of these George and Hannah are together, and the rest of them, George and Hannah, are not together. There's somebody else in between. I mean, think about just randomly putting these 6 people in the seats. George and Hannah will be beside each other, or they will not. That's a fact. There's no other option. And that means if there are 720 arrangements in total that include the ones where they're together, if we subtract the 240 in which they're together, we will get the number in which they are not together. I want to say that's 480. Let's find out. 720 minus 240. 480. So the answer to C is 480. Once again, the purpose of this lesson, I think, in my mind, is to give you more practice and exposure to seeing how some of these problems are done, and now to doing some of these problems. And remember what I've told you, I think, in a previous lesson, maybe I haven't, you're going to look at some of these assigned problems and go, I have no idea how to do that. We didn't do one like that, but maybe we did, and it's just written a little bit differently. Or maybe we didn't, and you have to figure out a strategy. Anyway, that's it. That's all. In the meantime and in between time, take care of yourselves, and I hope to see you in class soon. Have a great rest of the day.